Hello, everyone. Sorry, I got a little bit ahead of myself and forgot to do the recording, but that's not too bad because we're just starting it right now. This is the last section of material for the course that is tested upon. Next week on Tuesday, we will have our little review session. So please come with any questions that you have, like either on the worksheets or the homework, like the textbook exercises and stuff, along with your homework. And then we will on Thursday, we'll take our last exam. Tuesday of the following week, we'll go over voting methods, specifically the ranked choice voting. And then we will have our last day, which will just be on the quiz. And then as soon as you're done with that, you're all free to go, be on your merry way. So the expected value, by the definition, the expected value on a game, quote unquote, is the long run average. If the game was played numerous times. It is not the actual value of an attempt at the game, but rather what you should make/lose on each attempt. Whew. That's a lot to write. So we'll go ahead and explain it one more time. Since you're trying to write and listen at the same time, it's hard to do. So the expected value on a game is a long run average. If you were to play this game 1,000 times, like if you were go to a slot machine, which is based on probability, you were to play it 1,000,000 times, what would your expected value each time be? Are you expected to win about $1 each time if you played it 1,000,000,000 times, or would you be expected to lose about $20 every time? That's the question. And so the formula for it is that EV, expected value, is equal to probability number one times result number one plus plus last probability times last result. So you look at all the different outcomes of the game that you're playing, the game being whatever the game may be. So this is how you start to try and help your 6-year-old son or daughter person, how you can try and get them a little side gig to get some extra money, because the other kids won't understand the probability. So you give them this little game and they're gonna get a bunch of money. Get that extra money there. Don't actually do that. That's mean to do to children. But example, I think it's best to understand what expected value is. I think it's best done through an example. And I will provide this formula for you. You do not need to have the expected value formula memorized. That's the way it will be written on the exam. Is probability of number one times the result number one plus plus last probability times the last result. So here's an example of a game that you could play. Suppose a game costs $5 to play, where you roll a single six-sided die. If you roll a 3 or lower, you get nothing. If you roll a 4, 5, or 6, you get $4, $8, or $16 respectively. So if you roll a 4, you'll get $4. If you roll a 5, you'll get $8. And if you roll a 6, you'll get $16. What is the EV? Of this game? So this is the way I always like to set it up, but it's your prerogative. If you want to go straight to utilizing the formula, if your brain can think that way, awesome. Mine doesn't. So I like to have a chart that I can make. So this is the chart that I usually make for these problems. I'm going to wait for you guys to write this down before I actually start doing the solutions. It's way too hot. Suppose a game costs $5 to play where you roll a single six-sided die. If you roll 3 or lower, you get nothing, so you're out $5. If you roll a 4, 5, or 6, you get 4, 8, or $16. What is the EV? So the game is broken up into several different outcomes. That's the first row. And then the probability of that outcome. And then you have the result of that outcome. Probability and result. So the outcomes of this game, when you roll that six-sided die, based on the rules of the game, you could either roll a 3 or lower. You could roll a 4, a 5, or a 6. What would the probability of rolling a 3 or lower be? You could either roll a 1, 2, or a 3. There's 3 possible chances for that to occur, divided by 6 total chances. Because you could either roll a 1, 2, 3, 4, or 5, or a 6. So the probability is 3/6. The probability of rolling a 4, there's only one way to roll a 4, so it's a 1 out of 6 chance. Rolling a 5, also a 1/6 chance, and rolling a 6, also a 1/6 chance, because you only have one way of rolling a 6, and there are 6 total possibilities. The question is, what is the result? So one might say that the result of rolling a 3 or below would be 0, but I would argue that's not correct. The result of rolling a 0 would be a net of -$5. Because you paid $5 to begin with. Since you paid $5 to play. So if you play this game and you roll a 3 or 0, you're out $5. That's why the result is -5. If you roll a 4, you would get $4. So you'd only be out $1. So you'd lose $1. If you roll a 5, you get $8, but you paid $5 to play, so your net is a +3. And then if you roll a 6, you get $16, which means a net gain of $11. So now all we need to do, we've got the probabilities and we've got the results. We can just multiply them together and add them, and we're all good. So the EV will equal probability number 1, so 3/6 times -5 plus 1/6 times -1 plus 1/6 times 3 plus 1/6 times 11. Taking each probability and multiplying it by its result, and then adding all those things together. And if you plug that into your calculator, you plug that into your calculator, you should get negative 0.33 repeating. So approximately negative $0.33 when you round to the nearest cent. That is our expected value, negative 0.33. So to clarify here, so what does this number actually mean? What did we just compute? So our EV was negative. That is okay. This means we're expected to lose about 33 cents per play of the game if we were to play it a lot. We would lose about 33 cents on average. So that doesn't mean that on the next go, we're going to lose 33 cents. That's not possible. But if you were to look at our long run average, like first time we roll a 3, we get $0, so we're out 5, but then we roll a 6, we'd get $16. So that means that right now we are in the green by, so we lost $5, then we gained 11. So we're at a net $6 gained. But then we roll a 4 and we lose $1, and now we're at, now we're still in the green, but we've lost $1, so we're at $5. Then we roll another 3, or we roll a 2, and now we're back at 0. So if you were to play, like each time you play, you're going to either get losing $5, losing $1, gaining $3, or gaining $11. But if you were to look at our long run average, every single time to play the game overall, we'd probably lose about 33 cents each time. So that's what the expected value of the game is that on average, if you were to play this 1,000,000 times, realistically, each time you played, you lost about 33 cents. So this game is not in your favor. If you played it 1,000,000,000 times, you'd lose, like you're expected to lose about 33 cents per time in the 1,000,000,000 times that you played it. So this is not a good game for us. We want that expected value to be positive because that would mean that on average, we'd be winning. And as you could imagine, at the casinos, the expected value for you is always negative. The house always wins. That's the saying, right? Because they have rigged their games so that the expected value is negative. And that might seem frustrating, but remember, they're a business. They got to be making money. Ideally, they're trying not to make too much money. They're trying to make it a fun experience for us. But what are you going to do? So let's do another example. Unless there's any questions on that. I guess it's a weird concept at first, but it's saying like what should happen is that by the end of 5 billion plays, you'll have lost about, so 5 billion plays. Sorry, give me 1 second. Let's just do 5,000, make it a nicer number. So if you were to play this game about 5,000 times, you'd probably be out about $1,650. So that would lead to about a 33 cents loss each time on average. Trial number 65, you lost $5. Attempt number 1,048, you probably won $11. Attempt 4,999, you won $11 again. And then on attempt 5,000, you lost $5 because you rolled a 1. So each time it was a different amount. But on average, if you were to take the average, you lost about 33 cents per game attempt. That's what that's saying. So as another example, a game costs $2 to play. Sorry, the problem statements here are always long. If just so I'm still I've written several of the problems for the exams and I'm trying to narrow it down, but I wanted to ask you guys on the formatting. Would you like me to list all the results in a bulleted list on the problem? Would that help make it easier readable instead of just writing it all like in a paragraph?
Yeah, because we would have had to pull each thing.
Yeah, so it would all be right there. Okay, so I'll make sure that it's a bulleted list for any problem. There's certain examples of problems that don't fit into that mold, but I'll explain those ones. So the game costs $2 to play, where you draw a card from a standard deck. So a standard 52 card deck, no jokers. If you draw a queen, you get $20. An ace, $10. Semicolon. A male face card, $5 winnings. An even card, $1. And then an odd card, nothing. What is the EV? That takes a while to write. So feel free to take your time. We'll write down the solution in just a moment. The little advertisement here says keep our restrooms clean. I'm using this room for a restroom. Make sure you flush the toilets in here after using. And then wipe any excess water from around the sink areas of this room. There's apparently lots of sinks in here. I think that belongs somewhere else, but we'll see. So this is this should cover every situation. You either draw a queen, an ace, a male face card that gets rid of all the non-numbered cards, and then even cards and odd cards that takes care of everything. So what is the EV? Let's write down that little chart. You don't need to, though. You can figure it out as you go along, but this really helps me work through it. So there's the outcomes, there's the probability, which I'm just going to write prob, and then result. So result number, outcome number 1 is you would draw a queen. And it doesn't need to be super technical or whatever. You could just write Q. And for ace, you could just write A or ace for the next outcome. And then male face, or you could write MFC. Whatever you want to do, and then even card and odd cards. So now we need to fill in the probabilities. And this is a good chance to practice your probabilities. Remember, there are 4 suits and 2 red, 2 red, 2 black. There's a jack, king, queen, and an ace, and then there's 1 through 10. Or there's 2 through 10, excuse me, not 1 through 10. So queens, there is 1 in each suit. For suits, that means there's a 4 out of 52 chance. And you can fill in row by row or column by column. It doesn't matter. This time, let's do column by column. If you draw a queen, you get $20. So that would mean a net winnings of $18 because $20 to winnings, $2 to play, net win of 18. And I'm going to stop writing the number, the dollar sign, just because let's save ourselves some carpal tunnel. An ace, same probability. Drawing an ace would just be 4 out of 52 because there's 1 ace in each suit, 4 suits. That's a 4 out of 52 chance. And if you draw an ace, you get $8. So that's a net winnings of $8. Male face card, that's a jack or a king. So that's 2 cards in each suit. And there's 4 suits, that's 8 different cards, 8 possible cards. 8 out of 52. And winning $5 when it takes $2 to play, that's a net earnings of $3. An even card, there is 2, 4, 6, 8, and 10. So there's 5 even cards in each suit. 5 times 4 suits, that's 20. And if you were to draw an even card, you'd win $1, but it costs $2 to play. So that's a net loss of $1. And then an odd card, there is not a 1 because the 1 is the ace. So you 3, 5, 7, and 9. There's 4 odd cards in each suit, 4 suits, which means there's 16 total odd cards. So 16 out of 52. And if you get nothing, that means that you're out $2. How about Kimori? This is how much, got about 1.5 pages of notes. Before this problem, that is. So the expected value is just going to be multiplying each probability by its result and adding them all together. EV would be 4 over 52 times 18 plus 4 over 52 times 8 plus 8 over 52 times 3 plus 20 over 52 times -1 plus 16 over 52 times -2. So if you plug this into your calculator and you round to the nearest cent, you should get approximately $1.46. $1.46. Boom. So this is a good game for us. If we were to play this game, we absolutely should. We should play it as many times as we can because we are expected to win $1.46 each time we play. Now that doesn't guarantee it. This is expected, not actual. That, like if it said actual value, that'd be a lot different. We could be the unluckiest person on the planet, and every single time we played, we drew an odd card every time. And so every time we lost $2. But based on probability, that's not likely. there are very few people who would play this game 1,000 times and each time draw an odd numbered card. Or you could be the luckiest person in history and draw a queen every time for 4,000 times and get $20 each time you played this. But that's also not that's not realistic to what would actually happen. So the expected value is that you win $1.46 each time you play, not the actual. So the point being there is don't take this as what you should get, but rather what you are expected to get based on math only. Provided the person isn't trying to swindle you or whatever, trying to, not a weighted card deck, but like maybe they're one of those people who are really good at shuffling cards so that like you don't even see them put the queen on top or whatever, or queen on bottom. So we can do some fun bonus questions too. So bonus question on this problem. Part one is, if you played this game 500 times, what could you expect to walk away with? Now you can do this without doing dimensional analysis or unit conversions, but I love unit conversions, and I'm basically going to try and make it like Kill Bill. Like, if you guys ever saw Kill Bill, did anybody see it? It's been a while. It's a good Quentin Tarantino movie. One of my favorites. But there's a scene in it where in Kill Bill Part 2 where we learn her training and where she has to punch a wall, and so like from finger length away, just to keep punching a wall until she can punch through it. And she does it so much that in the middle of the night she wakes up and punches her wall. She was dreaming about punching a wall. I want that to be you guys with dimensional analysis. I want you to wake up and do a dimensional analysis problem. I want that to be, I got a cold sweat saying, no, I gotta know this. I want that to be you guys. Because dimensional analysis is so fun. It's so useful. And it can really just make you the belle of the ball at different parties. So the solution here would be, you've got 500 games. You're playing 500 games, and you're expected, for every one game you play, you get $1.46. So that ends up being roughly 438. It should be a little bit more than 500. I originally chose 300, but I decided to do 500 instead this time. 1.46. You should get $730. So pretty good. I mean, it took 500 playthroughs of the game to get $730. Expected. Could be a little bit more, could be a little bit less, but expected to win about $730. And then part two, suppose you can play one game every 11 seconds. Like, this is one of those kiosk games at like the bars and stuff where they have like a little, that was the weirdest thing on, like, one of the weirder things moving here. Like the fact that like grocery stores have a casino, and then also bars have typically a little casino. That was definitely weird to see. But so like, imagine this is just one of those games where you can keep mashing that button as fast as you want, and you can play this game every 11 seconds. What would your hourly wage be? So if you wanted to take this up as your job, you just sit down at this computer and play this game 1 billion times a day. So you need your dollars per hour, right? So there's a lot of different ways you could start this, but I'm going to start with my original thing of saying I get $1.46 for every game that I play, for every one game. Expected, not actual, but expected. So that will get me my amount per game, but I want my money per hour. So I need to get rid of the games, but I know I can play one game every 11 seconds. So one game up top, 11 seconds. And that'll cancel the games. And so now I have dollars per second. So we're close, but we want dollars per hour. So we need to convert those seconds to hours. So we know that there are 60 seconds in a minute. So we'll put the 60 seconds up top so we can cancel the units diagonally for 1 minute. And the seconds cancel. But that's dollars per minute. We want dollars per hour. So we will change this and say, so 60 minutes to every 1 hour. And then the minutes will cancel. And then if you look at it in the numerator, we've got dollars. Denominator, we've got hours. We've got our hourly wage, dollars per hour. And if you plug this into your calculator, so 1.46 times 60 times 60, divide that by just 11, and you get approximately, if you round to the nearest cent, approximately $477.82 per hour. So if this existed, I'm quitting my job. Especially since this is all played on a like you're gonna get the cash out, you're just gonna get the cash. That's tax-free, guys. Just a little bit, just a little tiny bit of tax evasion. Just a little sprinkle of tax evasion in there. You know, government doesn't need to know. Government doesn't need to know. Not that I'm condoning that. Like hypothetically, I might have been a tutor and gotten cash. I don't know, that seemed like free money to me. Not that I actually ever did that, by the way. Never did it, actually. Oh yeah, sure.
Simple first problems.
Yeah. Absolutely. For real, I didn't actually do that. See, I don't have my face recorded, so that's okay. I can do that. Just a tiny bit of tax evasion. Who are they gonna care? I mean, granted, if you played this game for 8 hours a day, what will be your weekly take home if you worked 40 hours a week, right? Times 40. That's $19,000 a week. Multiply that by like 3.5, right? Because it's roughly about 3.5 weeks in a month. That is $66,000 a month. Tax-free too. No. So let's divide by 3.5 and multiply it by 52 for your yearly salary. That would be just shy of $1 million. Just shy of $1 million. Granted, you'd have to play this game every 11 seconds, just mashing that button for 8 hours a day. Right? I mean, I'd take that. I'd take that for maybe a year and then live off the $1 million, as we saw. Remember, like if you put that in investing in something that's giving you an annual return of like 10%, that's $100,000 income right there, just by passive income. Most BS thing ever. Anyways, I'm getting sidetracked. Let's get back to it and do another example. So this is one where I wouldn't be able to put a bulleted list, but rather give you a chart example. A game is played by spinning the following wheel. What is the EV? So, and like, there'll be a couple problems like this on your homework, and like, it will either be implied what the pi percentage is, or it will tell you. So, and on an exam, if I were to do this problem here, I would definitely tell you what each percent, like what each one was. So it's divided like this. So right down the middle, then on the right-hand side, it's directly in half. And then it is this, like a small sliver. And so in this game, there's no pay to entry. It's just if you lose, you have to pay the person who gives you this game. So if you roll into this one, which is a 12, like you win $10. That's a 12.5% chance. If you roll here, you lose $3. And that's a 37.5% chance. If you roll in the top right, you're going to lose $4. And that's a 25% chance because that's a quarter of the circle. And then if you roll in the bottom quarter, you win $8. That's a 25% chance. So this one, there's no bulleted list, but it's all right there for you, right? Nice and neat. So we could write the like we could write down the outcome probability result if we really wanted to, but it's all there for us. We don't need to do that, especially since the probabilities are already there. I know they don't look like probabilities because we're used to seeing them as fractions, but remember, every fraction, every probability can either be listed as its fractional version or its decimal percent. So 25%, that's a 0.25 chance. That's a 1 in 4. 12.5%, that's a 1 in 8 chance, and so on and so forth. So you can convert these percentages to their decimal equivalent to get your probability. So the EV if you land, and you can start however you want to. I'm going to start with the win $10 and move around. So you could win $10, and that's with a 0.125% or 12.5% chance. Plus, you could lose -4. So you need to write -4 because you're going to lose that amount times 25%, so 0.25, plus $8 times 0.25, plus -3 times 0.375. Does anybody have any questions on like I wrote that in the wrong order. I should have wrote the probability then the result, but because multiplication is commutative, it doesn't matter which one comes first. But I technically should have wrote 0.125 times 10, and then 0.25 times -4, plus 0.25 times 8, plus 0.375 times -3. But it all works out the same. Any questions on how that's set up? All right, if you plug that into your calculator and you round to the nearest cent, that should be roughly $1.13 for each game played. Once again, a very, very good option. This is a good game for us to play because the odds are in our favor. If the expected value is positive, that means that the game is going to hypothetically win you money if you were to play it 1 billion times. If you only play it like 5 times, it's not expected that you're going to win that much or lose that much. But play it 1,000 times, each time you'll win about $1.13 on average. One more example, and then we'll talk about fair price. Unless there's any questions on that. These numbers, like these calculations, by the way, especially when they involve the fractions, they usually have a lot of different outcomes. So take your time entering in your calculator. Make sure you've entered it in all correctly. My recommendation, honestly, would be to calculate it once, write down your answer, and then do it again to make sure you get the same answer. And if you don't, then do it one more time and see which number gave you the right answer. So anyways, this is one of them. Example, CSN is like hosts a raffle that costs $2. $2 to enter. The first prize is $1,000. Second prize is $500. And third and fourth place is $100. Sorry, 1 second. Still need to write more. Find the EV if tickets are replaced each time and 5,000 people are in the raffle. Assuming that you can only buy one ticket. So hypothetically, there could be games where you could buy multiple, but let's just assume you're only allowed to do one of them. There's like I'm going to ask a bonus question after this one as well. So if you've ever wondered how schools utilize raffles, we'll wait until this one's done. So we're assuming that each time a ticket is drawn, it's put back into it, shaken up, and then another one's drawn. So it is possible for a person to win first, second, third, and fourth prize. However, with 5,000 people, that's highly unlikely. But anyways, solution. We'll write our outcomes, our probability or prob, and then our results. So the results are either first place, second place, third/fourth place, because they end up being the same amount, but you could write them as two separate entities as well, and then you could lose. The reason why I said replaced each time is that if we don't, we'll write down the probabilities in just a second. So the probability of being first, there's 5,000 tickets. There's only one way to be first. That would be a 1 in 5,000 chance. Then the next ticket is drawn. There's still 5,000 tickets, and there is only one second place winner. So that's a 1 in 5,000 chance. Third and fourth, each one separately, you could write them as 1 over 5,000 plus 1 over 5,000, but it's not going to be a matter. You draw it both times. There's a 2 out of 5,000 chance to be third or fourth entry. And then losing, there's only 4 winners, and the rest of them are quote unquote losers, which would be 4,996 ways out of 5,000. Because only 4 people win, that means that the rest of the people, 5,000 minus 4, which is 4,996, will lose. Now, since the raffle costs $2 to get into it, if you get first prize, your net gain is $998. Second place, you get $500, so your net gain is $498. Third and fourth, your net win is $98. And then if you lose, you're out $2. And that's it. So not a bad idea to play this game. So what would your expected value be of playing this game? That would be 1/5,000 times first prize, $998, plus 1/5,000 times 498, plus 2/5,000 times 98, plus 4,996 divided by 5,000 times its result of -2. And if we, I'll let you write that down. So if you plug this into your calculator, you should get roughly -$1.66. So this is rigged in CSN's favor, but I would assume this is for a fundraiser. Now, this problem has the bonus question that I'm going to ask has nothing to do with probability. And it's just basic mathematics, but it's an important question to ask. Bonus question. How much money will CSN raise for the in this raffle? How much money will CSN raise in this raffle? So, how would we figure this out?
So it's $2 an entry and expected to gain $1.66 from the entries.
Yes. So yeah, there's a lot of different ways. Like there's a million different ways we could think about this, and that would be true. That would be one of the ones I would do. But this means like the key thing here is $2 per person. You have 5,000 entries, so $2 per person times 5,000 people. This would be their revenue, not their profit, because remember they have to pay out $1,000, $1,000 to one person, 500 to another, and $200 to the other two people. So minus the prizes, because they have to divvy these out. So that's $1,000 to plus 500 plus 100 plus 100. So that's 10,000. Minus 1,000 minus 500 minus 200. And you get $8,300. Come on, there we go. So that's how we would figure out their net gain here. So like if this was for a raffle, that's a pretty like as long as all 5,000 people were willing to just chip in $2, and then with the hopes that you're one of the winners, you get like you might win $998 or $498 or $98. You probably lose, but it's for a good cause. It's for this is for the in the what was the thing with the in the arms of the angels? What that song is always associated with one. Yeah, with Sarah McLachlan, right? I think the ASPCA. Yeah. So it's for a good cause. I don't want to see those commercials. Those commercials hurt my soul. Don't send me pictures of sad animals. That's super sad. But that song will forever be connected to that concept for me. Anywho, so that's a sizable chunk of change to donate. But anyways, we'll get started with the concept of fair price. So fair price is just closely related to expected value. So fair price definition. The new section. Fair price definition. The fair price to pay. Fair price to play, excuse me. I'll put to play in parentheses because it's assumed when you say the fair price, you're assuming you're saying the fair price to play the game. The fair price to play a game is the price point where the EV equals 0. So how much should you charge a game so that it's fair? Meaning that if you were to play the game 1 billion times, hypothetically, you would come away without having won anything or lost anything. So like, I mean, like there's that whole thing when you're playing like a game, you're like, I gotta end on a hot streak, or I gotta end on a good note. Or just try, like me personally, whenever I go to a casino just to have some fun, my assumption is I'm gonna lose it. But if I can get back to where I started, that's a good news. That I got to have fun and I didn't lose any money. That's the way I like to think about it. But that's what the fair price is what would you need to charge to make sure that every single time you played, you net lost about $0 or net won about $0. So to figure it out, assume the game costs nothing, costs $0, and the EV you get will be the fair price. Let's write that down and then let's think about why that's true. So in unlike this situation with the chart where there was no price to the game given, and it was just like you had to give the person that money. Instead, imagine in actuality, there's going to be a cost to playing the game. There's going to be a cost to playing a game. So hypothetically, like if you look back at the previous situations, if I didn't mention like this one here, if it didn't cost $0 to play, or if it didn't cost $2 to play, then you would either win $20, win $10, win $5, win $1, or you didn't get anything at all. You got 0, and there was no loss ever. So if you did it that way, you would find the expected value of playing the game each time, and each time it would be a positive number. So like each time you'd either get 20, 10, 5, $1, or you wouldn't get anything. So once you find the expected value there, that's how much you are expected to win each time. And so if you're the person creating the game, you want to make sure that you net, like you keep those losses, like you make up for those losses. So the expected value from not charging anything for the game gives you your fair price. Does that make sense? I can explain that again, maybe in a different way if need be. But assume the game costs $0 to find out the expected value if you could just play the game for free, and that expected value will be your fair price, because that would ensure that on average you net lose nothing. So as an example, A carnival game has a basket of 4 envelopes in which a player picks 1. So you're just given 4 envelopes. They're put on the table, and you pick 1, 2, 3, or 4. Kind of like the Monty Hall problem, where there's 2 doors that have a sheep, 1 door that has a car. Except these ones, there's 4 envelopes. The envelopes contain $1, $10, $20, or $50. So one of those ones has a George Washington, one has a Hamilton or Hammy, one has a Jefferson or a Jackson, and one has what's the $50 bill? Who's on the 50? Is it Ford? Gerald Ford? This is useless information. Good old Benny is on the 100, but I forget who's on the 50. I think it's Gerald Ford. Terrible president. Terrible president. He essentially let, if I remember correctly, he essentially let just slavery continue. Like he didn't. There was a word from U.S. history, but what is it called? His thing was like the separate but equal. Like he said, let's just segregate you. It's terrible bullshit. Excuse my language. I just remember having to do a book report on him. Wait a minute. Okay. Anyways, so let's assume that you pick an envelope 1 to. So was it Ford on it? Grant. No, Ulysses S. Grant. That's the guy, not Ford. Grant. That was the bad guy. That was the bad president. But anyways, what would a fair price be? What will be a fair price for this game? So we're going to assume that starting off that it costs 0. So obviously, no matter what you do, you're going to be net earning money. So solution, outcome, probability, prob, and then results. So you could pick envelope number 1, envelope number 2, envelope number 3, or envelope number 4. And just to make it easy, let's assume that envelope number 1 had the $1 bill, envelope number 2 had the 10, envelope number 3 had the 20, and envelope number 4 had the 40 or the $50. So the probability, since it's completely random, there's only 4 envelopes on the table, and you can pick one of them each. So each one has a probability of 1/4. And you would either win $1, $10, $20, or $50. So the expected value here would be 1/4 times 1 plus 1/4 times 10 plus 1/4 times 20 plus 1/4 times 50. And remember, this is a completely fabricated game. It probably would be that there's 10 envelopes that have a $1 bill and 1 envelope that has a 50. But either way, let's just assume this crazy game exists. And so then this would be $20.25. So if the game costed 0 or costs 0 to play, you'd be expected on average, if you played this game a million times, each time you'd be winning about $20.25. So the fair price is therefore $20.25. Who would want to play a game where you had to pay $20 to play? Box. Give me a box. There we go. So that's how you would want to do it. You want to make sure that the fair price for this game would be $20.25 per entry. If you did that, you would get a net result of 0. And you can even verify it. Just change the results and say, okay, if you drew envelope number 1, you gain $1, but it costs $20.25 to play. So your net loss would be $19.75, right? Wait, no, minus $1 from that. 19.25. Yeah, so you'd be out $19.25. $10, you'd be out $9.75. 20, you'd be out 25 cents, and 50, you'd be out $29.75. And so if you do that, if you multiply those numbers by the probabilities, I guarantee you your EV will be 0. So that's a cool thing about this problem is you can verify your answer by redoing it, but changing it so that you actually take into account that price for the game entry. All right, any questions on that? Let's see here, I got 2 more examples. All right. So example, a school has a raffle with a prize of a $200 Dave and Buster's gift card. $200, that sweet D&B, right? And the D&B gift card. Might as well just give me a piece of paper. I'm not going to go to Dave and Buster's. No, I would totally do it.
It's fun.
Yeah, no, I'm kidding you. I'm totally kidding. I would play the hell out of Metal Slug. That was my favorite game. Metal Slug is awesome. Metal Slug and Reed, the game with the ship, and you get the upgrades and it starts to shoot more lasers. Oh, so fun. So fun. Total aside, just thinking about fun. Because I didn't. So my wife and I bought a Lego set at one point. We were trying to this is completely not important, but it's important for your own well-being. Lego has a free app called Lego Builder that allows you to play with to build Legos with other people fairly. It's how like back in my day, we didn't have smartphones. And so if you wanted to build a Lego set with your friends, you would have to be like, okay, I get to do page 1, then you get to do page 2, then you get to do page 3, and so on and so forth. So there's a point where you're just sitting around doing nothing. And if you want to be nice, you would have to you'd find the pieces for them and give them to them. But this way, what it does is it literally just has you working on the same thing at the same time, but working on different pieces, and then you build them together. You might start building the main piece, and you get it, and then it'll pop up on both of your guys' apps saying it's time for you to hand over the big piece to your friends so they can work on that. And then you start working on a little tiny piece. And it's completely fair and awesome. I didn't even know that it's free. It's just granted, you have to buy the Lego set, right? Which costs an arm and a leg. But you can do it for any Lego set. They've got them all online and the algorithm works, which is so cool that it's just free. That's awesome. So good guy Lego for giving you that free gift, in addition to buying a $700 AT-AT set, or I guess technically the AT-AT, if you're a big Star Wars fan. But one of my friends is big into it and told me it was a $700 Lego set. I was like, damn. But then again, it's this big and it's a perfect replica of an AT-AT. So limited edition too, apparently. Anyways, so school has a raffle where the prize is a $200 gift card And that's it. Only one person gets it. If the school intends for the event to be fair, what price should be charged? If there are 1,500 students, 1,500 students. Great, to kind of mess up to make them pay money for this raffle that's supposed to be for something, but whatever. So we're going to start by assuming that you just enter it for free, for frizzles, and then see what happens. So we only have two outcomes. You either win the $200 D&B gift card and you can bust out some Dance Dance Revolution, some DDR, good times. Or play, does anybody remember Hydro Thunder? Hydro Thunder. Does that ring a bell for anybody? I just remember that game all the time. And that was the way that like it like played that sound clip way too often. Anyways, so solution. We could write it, but we don't need to. There's only two events. You either win. So the EV, if you were to not charge anything, there is a 1 in 1,500 chance to win the $200 gift card. And then there is a 1,499, so 1,499 out of 1,500 chance that you do not win anything. So you get $0. And if you plug that into your calculator, you will get 0.133 so approximately 13 cents. So you're really going to make some people bust out either a dime and 3 pennies or 2 nickels and 3 pennies. Or if you're me and you want to stick it to the man, bring 13 pennies. One of them being a Canadian penny. Hopefully they won't notice. This Canadian money's not real. Silly Canadian. So that would be a fair price, hypothetically. Last one, just to add a little bit of spice. Let's make this one a little bit. Actually, this game does like this one doesn't actually make sense. You know what? This like I'm looking at this problem that I wrote, and it's actually it doesn't make much sense in actuality. So we're just going to skip it. It doesn't make any sense. So that'll be it for today then, I guess. So we're done 10 minutes early. Does anybody have any questions or want me to do another example? I can make one up on the spot if you really want to. They're all done the same way. You guys want to do another one? All right. Do you guys want it to be dice rolling?
Yes.
Dice rolling?
The sum of, I don't know. I was thinking-
Okay, gotcha. That'll be fine. Example. A game is played by rolling 2 6-sided die. Which costs, someone give me a number. $13? All right, $13 to play. If the sum is 12, you win $100. The sum is between 5 and 11. You win, let's do $25. And if the sum is less than 5 is strictly less than 5, you get nothing. Find the EV. So notice this is not a fair price question. As soon as you see the word fair in the problem, that's talking about fair price. I will make sure, like, so on your homework, that might be the case that happens. I will make sure that on the exam, if there's a fair price problem, I will say IE. Like if I say what will make this game fair, IE, and like in parentheses, what is the fair price of this game? But find the EV. So we would need to resort to our chart here because I don't know this one off the top of my head. If there's a problem on the exam that involves rolling 2 dice in the sums, I'll provide that chart again. So like I won't highlight anything like that, but I will provide it because that's otherwise like you'd have to just figure it out and that's just not fair. So I'm just gonna be right back and grab that. That was from 4.3. Let's grab that. Copy it. So we'll just use this for reference on this problem. Make this smaller. While you're still writing it. The other thing I got to do is I got to erase these. You might be thinking I'm erasing it, but look, it just erases. It does it in 2 steps. It erases the highlighting and then the other thing. So for the solution, does everyone have it written down? All right, solution. We'll do our little chart. We'll do outcome, probability, and then results. So you could roll a 12. You could roll a 5, the sum being between a 5 and 11. And then you could roll a 1 through a 4. So the reason why I wrote the sum there, by the way, is that otherwise I see these as just numbers and my mind will, like, if I'm not paying attention or if someone sneezes while I'm taking the exam, I might forget what I was doing and just do 12 times your probability instead of your probability times the result. So if you write it as like sum is 11 or sum is 12 or whatever, that might help you avoid that circumstance. So looking at this chart, there is only one way to roll a 12, rolling a 6 and a 6. So there's 36 possible outcomes. Once again, that 36 is coming from the fundamental counting principle. There are 6 outcomes for your first die roll, 6 outcomes for your second. Multiply this together, that's where you get the 36. So, and I'm going to go column by column this time, but you can also go row by row. It does not matter which one you do first. But if you were to roll a 12, you got $100, but it's $13 to play. So that's 100 minus 13 is $87 net. 5 and 11. So I'm going to even highlight it on this graph. So sum is between 5 and 11. So that is from here onward. That's all of these ones here. So we'll have to count those up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. So there's 29 out of the 36 chances that that happens. And if you were to do this, you would win $25, but you paid $13. So that's a net winning of 13 or 12. And the good news is the last one, you don't even need to calculate. You can just do, it should be 6 because you've taken care of all of them except for the last situation. So 29 plus 1, that takes care of all the other situations except for the last ones. But you can also just do it by counting 1, 2, 3, 4, 5, 6. So a 6 out of 36 chance to lose, which means you'd be out $13. So you'd be a net loss of 13. So yeah, I will provide, like, if I decide to include a problem that involves rolling 2 dice, I will never do more than that. I won't do like I won't do like rolling 4-sided die, 2 4-sided or 2 D20s. That would just be obscene because I have 400 entries. Though maybe if my son makes me angry, then I'll make it a rolling 2 D20s. How about that? No, I'm kidding. I'm kidding. So at most 2 6-sided die. So EV then would be probability number 1 over 36 times your net result of 87 plus 29 over 36 times 12 plus 6 divided by 36 times negative 13. And if I plug that into my calculator, 1 over 36 times 87 plus 29 over 36 times 12 plus 6 over 36 times parentheses negative 13. Now I do that, my expected value when I round to the nearest cent is 9.92. Not a bad game. Very, very heavily swayed in our favor. We're expected to win roughly $10 every time we play that. I didn't realize that making the sum be between 5 and 11 would take care of basically everything. So, anywho, any questions on that? Yes. Because the game costs $13 to play. And so you lose $13 if you win, like you lose and don't get anything if you roll a 1 or 1 through a 4. So that would be a net loss of $13. All right, guys, that'll do it for today. That's the last bit of material that's tested upon. On Tuesday of next week, we'll come back and we'll do a review. So come with any questions you have, anything you want to do more of, please let me know. And then on Thursday of next week, we'll take our last exam. And then on Tuesday of the following week, we'll take we'll go over voting theory a little bit, along with any review you want to do, and then for the final quiz, which is on Thursday of 2 weeks from now. So next Thursday exam, so a week from today exam, 2 weeks from today doing the final quiz, and that's it. If you have any questions about that, feel free to email me. Otherwise, you guys have a great day and a great rest of your a great weekend. See you then.